these beautiful objects of it in an exact form, you need to compress things. Oh yeah, recordings. So what to compress? And so far we were compressing value functions. And we had a great time there trying to figure out what is possible, what is not possible in an efficient way. And the other option is to compress policies, right? I don't know whether there is any other. Okay, yeah, like there is, obviously. You can compress the MDP. I think we made very, very small excursions into that theory, into that territory, if you wish, in one of the homework assignments, like on the side, let's just prove that, well, if the MDP is compressible, then you're in this very beautiful world and everything works. So we like to pick up the harder tasks. So that's why we talk so much about value functions and policies and how to compress those. But you can do great things with compressing MDPs. And maybe I'm going to come back, but then the danger is that I will never finish this planning part. Okay, anyways. So what to compress? Policies. That's our target now. So how can that work? Well, if you have an MDP and it's too large, state space is too large, maybe it's discounted. At the end of the day, what you are interested in is a policy, right? So you might think that, okay, what not? Like, why don't we just compress policies? That means that you're going to select a subset, generate the memoryless policies. So ML just meant this is this set of memoryless policies. And in general, you want a strict subset. You want a small subset. And one example for that would be when you have, you're going to laugh, a feature map. And the feature map takes a state action pair and returns a vector representation of this state action pair in d-dimensional space. And the associated set of policies could be like many things. One possibility is to just say that, you know, you take any policy pi, which is memoryless, such that for every 2 pairs of states and actions, if the features of these 2 state action pairs match, then it follows that the policy assigns the same probability to action A given S and action A prime given S prime. That is 2 state action pairs for SA and S prime A prime. The idea is that you have a set of state action pairs, and all that the policy can see, or all that like whoever's designing the policies can see, is this image of this in RD. And so they can act based on what they see, these vectors, but they can't do anything else. Okay. And So these this class is the same as if you say that you allow all value functions, all action value functions that are just a function of the features, and then the policy is going to be just this Boltzmann class. And the very special case of that is this Boltzmann linear class, where the policy is such that pi of AS is proportional to the exponential function of, I don't know, W transpose. I guess in the past I used theta, but why not? You have to change. So for some feature vector, sorry, so some weight vector W, the probability of choosing action A in state S is proportional to this inner product. You can think about this as a score, and you're just scoring all the actions. And then in proportional to the score, you're increasingly likely to select the actions. And there are many examples that people devise. So you can come up with other functions here. This thing, it doesn't necessarily have to be linear, and so on and so forth. So there's a large number of possibilities. So, and then the most obvious question to ask, are we going to be able to efficiently search within this class of policies for a policy that is kind of like best suited to our purposes? Where what could be our purpose be? Well, one possibility, I mean, if you're doing planning, then maybe you think that, okay, I have a distribution over the states. Maybe it focuses on my current state. And then I devise this objective function, this value function for the policies, which is going to assign a value of j to a policy pi, which is simply going to be the expected value of the value of policy pi, right? So the value function, V of pi assigns a value to every state, and so this is just a shorthand notation. Actually, I'm going to get rid of this transpose. So note that every distribution is just a row vector. We stick to the finite case. It's easier to imagine things and easier to follow what's going on. So this is just like saying that, well, with probability mu, I jump in state S, and then from then on, I'm going to follow my policy, and I collect all these rewards. They get discounted. I sum them up, take the expected value, and take the expectation over the initial state as well. So it's like the total expected value if you're starting from this distribution mu. And then you might be wondering about, okay, like, is this, can we solve this optimization problem, please? That you want just to maximize this value, right? Can we do this efficiently? So this is the question of policy search. And then this is the first question to ask, like, can we efficiently do this. You have access to a simulator or the MDP or whatnot. You just want to do this. What do you think? Is this an easy problem? Is this a hard problem? It's computational and query efficiency question. Well, I guess I should be a little bit more specific. Let's say you're in the Boltzmann class, the Boltzmann linear. Which is basically, by the way, so this Boltzmann linear class, where is this? The W's can go to infinity, so it's like it's better to take its closure when you let the W's, like their norm, go to infinity. And then you get an interesting class. Well, if you were doing state aggregation, for example, so phi is phi SA is like this feature vector for private feature vector for every action A for the states, which just differentiate between whether the state belongs to a group, so state aggregation. So then this Boltzmann linear would be like for every part in a partitioning, and this state aggregation is partitioning of the state space, you have to come up with a probability distribution. So for the first part, you need a probability distribution. For the second part, you need a probability distribution, and so forth. I of k is just a probability distribution over the actions. Just to make this a little bit more specific, and let's say, okay, we are sticking to this like state aggregation Boltzmann linear. So we saw that for, wow, did you see that? State aggregation is really beautiful, right? So if you do value function approximations, like pretty much everything is going to work. Maybe there should be some homeworks about this. I don't think that we really spell this out, but that's a very, very beautiful case for value function approximation. With the Polytech proof, or even some modification of API, things are going to work well. How about this? Can we solve policy search? Okay, I need votes. All right, you type in the chat. If you think that you can do this efficiently, computationally efficiently, say yes. Otherwise, say no. Right, type. We just want to know, like, how people feel about this. Okay, yes. Don't do, just type. Cool. Okay, 2 more yes. Come on, people. Depends on init. Oh, well, you're not allowed to type that. You're allowed to type yes or no. Yeah, okay. Come on. All right, more. The 28 people here. Okay, yes. Yes. Good. You will feel good about it if you type something, so just do it. It's good. This is the way to participate. Okay, come on. It's not marked. Efficient as in polynomial, yes. Roshan says no. Come on, Roshan. Can't be that negative. Ha. Yes, so it's efficient as in polynomial. Let's say in the size. Okay, I make this easy, right? Like I allow complexities to scale, not with the number of partitions, but even with the number of state action pairs. So it's not about compression, it's just computation. Like, can you do this? So Vlad, what do you think given my answer to your question? So yes or no? All right. Okay. It's a no. No. All right. How does this work? I think that this is a very cute result. It's from a paper by Nikos Vlasis. Michael Littman and David Barber. And they didn't talk about function approximation or policy search or whatnot, but that is what happens to be applicable to this case. They were talking about PUM-DPs. So PUM-DPs are hard, and thereby policy search is also hard. Connor wants to remind. It's too late, Connor. But if you want to defend yourself, speak up. Okay. All right, so how does it work? How come? The example is known as blind policy search. We are trying to find a policy which, independently of the state, chooses a distribution. Okay, so it's state aggregation with a single partition, like a single group of states, single part. So phi SA has as many dimensions as the number of actions, and everything only depends on which action you choose. So in other words, this policy class can be identified with the distributions over the actions, over the A actions. So blind policy search asks for what is the best policy in this class. So just to make sure that we understand, here's the state space, you're at the state. You choose a distribution, pi, and you're in this other state. You choose the same distribution, pi, well, the dynamics is going to influence where you go, but like you just choose this same distribution no matter where you are. And the example that is going to show hardness is going to be an MDP, that there are the same number, let's say n, states and actions. Okay. And to specify MDP, we need to specify what are the transition probabilities. And we're going to make this super simple. Whatever action you choose, you go there with probability 1. Okay. So this also means that you don't go to any other state ever. Right? So whatever probability distribution you choose, that means that it doesn't matter where you are, your next state distribution is going to be that. You can just like choose whatever probability distribution you want to see over the state space. That's your control. And we're going to choose the rewards later. So let's just see first, how does the objective look like? And then so we're going to choose, I don't know, this initial state distribution. Let's choose it to be the uniform distribution. Okay. So now let's see how this objective function looks like. Sorry, this is one transpose. So it's mu v of pi. And we know that v of pi is just the sum of the discounted sum of the rewards under policy, which you can obtain if you take, r of pi, and r of pi in this case is just, at s, it's going to be pi of I RAS. And so to calculate this, let's look at what the transition probabilities are from going under policy pi from state S to state S prime. So what is this probability? Can someone help me with this? What is this probability? All right, so Connor says that this is pi S prime given S. Okay, Mehran says is the sum of pi A given S, PASS prime. That's the definition. That's absolutely correct, Mehran. Connor, you said it's pi S prime given S. So what is pi S prime given S? I guess like maybe I'm not too specific about that. These policies, they're just a single distribution, right? Over the actions now, right? Because in every state you have to choose the same distribution, right? So and let's call that distribution just pi. Okay, so we identify this distribution with the actual policy. I don't want to give it a new name or anything. I hope it's clear. So given that, it's, yeah, let's say it's just pi of S prime. Yeah, that's right. Just writing the definition here, this is in general this, but right. But of course, in our case, this is just pi of A, and this was, you know, the indicator whether S prime is A. And so you're summing over all A's, but you only hit the jackpot when A is S prime, so you get pi of S prime. It's intuitive, right? So as I said, the next state distribution is exactly what we chose, pi. If I want to write this in a matrix form, well, I would write it as 1 pi transpose, right? So pi is just the column vector. And of course, if you take any power of this, any positive power of this transition probability matrix, what do you get? What's the next state distribution after 10 steps with this policy? Or 100? After 1 step, which is pi. After 2 steps, okay, what is it? Okay, 1 pi top for all steps. The matrix is idempotent. Sure. Yes. Well, we can just like use the definition or think about it, right? Like this was the case when the policy didn't care about what state it is at. So it will not matter that the next state distribution is already transformed to something. It never matters. These distributions are always the same. It's just pi for any t. All right. So now we are ready to plug in. What happened here? I think I'm writing in the middle anyways. Okay, so j of pi is going to be mu, and then there is this infinite sum. It has a first term. So this infinite sum, t equals 0. We get the identity matrix there. And gamma to the power of 0 is just 1. And then for all of these matrices, we get the same matrix, and then there is this infinite sum of gamma to the power of t, and I already put out the gamma, so it's gamma times 1 over gamma, gamma divided by 1 minus gamma, 1 pi transpose, and then r pi. And instead of r pi, let's just imagine that we rewrite this immediate reward as a big matrix. So the matrix R is going to be to contain the immediate rewards, that the row indices are by S and the column indices are by A. Because we were left multiplying with distributions over states, and we are right multiplying with a distribution over reactions. Okay, so if you just plug this in, and you get this beautiful expression. Oh, look at that. So this is going to be equal to, there is a first term. This is identity that multiplies R, then pi. Okay. And then there is the second term, mu multiplies 1. That's just 1 because mu is a distribution. So there, the mu goes away, and then there is gamma over 1 minus gamma times pi transpose R pi. And if you look at this, and remember that we want to maximize this over the simplex, over these probability distributions over reactions, like just simplex, then you can smell trouble. Because I can choose this matrix R in an arbitrary way. It doesn't have to be definite. It's just like, it's like a wide, crazy optimization problem over the simplex, right? So it's quadratic, but if R doesn't have any nice structure whatsoever, why would this have an efficient solution, right? In general, it doesn't. Well, if you think about it, okay, if R was positive definite, then this expression is convex and you are maximizing a convex expression, you would be lucky because that's going to be at one of the corners. If you want to prove hardness, that's not what you do, right? So now you can think about, oh, maybe I should be negative definite. Maybe that's a better idea. Well, that's not going to lead to a convex. So that's not going to lead to a hardness result. You need to get something indefinite, because then you flip everything, you're minimizing a convex function, and then you are happy again. So the hard case comes from when you're neither positive definite, neither negative definite, but you're indefinite. And how do we know that there are hard examples for that case? There is a beautiful theory, beautiful theorem in graph theory. So we need to do a little bit of graph theory. It's my excuse to talk to a nice connection to graph theory. So in graph theory, you have all these extreme problems of like, what is the cardinality of the maximum independent set? Right, so you have a simple graph which has these vertices, and there are no loops, no self loops, and it's undirected, and an independent set here is this neighbor-free set. I don't know why they don't call it like that. So it's like you want to select vertices such that if you selected a vertex, then all the neighbors of the vertex are forbidden to be selected. So now I can select this, but if I selected this, then there is nothing else to be selected. And you want to select the vertex set, which has the maximum number of vertices in it. So that's called the maximum independent set problem. It's one of the classic NP-hard problems. It's actually a really hard NP-hard problem. It's even hard to approximate to any constant factor. It's one of the strongly NP-hard problems. And it's NP-hard even if you have cubic graphs. So cubic means the graph is 3 regular. That means that every node has, every vertex has 3 neighbors. It's like nice and regular. And curiously enough, there is a result that connects the maximum independent set problem to maximization of quadratic expressions over the simplex. There is this theorem by Motzkin and Strauss. It's not new. It's like 65. That says that, okay, so the maximum independent, the current of the maximum independent set, that's denoted by alpha G. If you have this graph G with this vertices V and edges E, okay? So then alpha G is the maximum cardinality for a vertex set, which is independent in G. So the theorem says that, what does it say? It says that 1 over the independence number, so this alpha is called the independence number, of the graph is equal to the minimum over all the distributions over the vertices, the simplex. Let's say, okay, that's a bit too much. Just, ugh. So let's say there are n vertices. So then you take all the elements of the simplex, and if you're minimizing G plus I, the quadratic expression underlying G plus I, where G is the vertex adjacency matrix of the graph. So that's overloading the notation, but it's kind of the standard thing to do. So recall that this matrix is an n by n matrix such that Gij is equal to 1 if and only if I and j are connected in the graph. There are no self-loops, so Gi is here. Okay, so there is this theorem, and this tells us that, yeah, maybe this maximization problem is hard. Well, how come? Well, this other problem is a minimization problem, but that wouldn't stop us, right? Because we can just choose R to be the negative of G plus I. So it is going to be a reduction, right? Like, you're going to say that, well, if I can solve the blind process search problem, then I will be able to solve the maximum independent set problems in 3 regular graphs. And the way we do this is that we are encoding any such three-regular graph into an MDP. So if you pick a graph, G, which is three-regular, then we can, so pick this G, which is three-regular, and we want to use our policy search method to find the maximum independent set. How do we do this? Well, we need to choose. So we see this curious similarity here. We need to choose some R. And here we have a minimization. Here we have a maximization. So the natural choice is going to be what? Can someone help me? What's the natural choice? For the thing that you would try first? How to choose R? Any wide guesses? Negative of I plus G. Okay, let's do that. Thanks. So let's try R to be equal to negative of I plus G. This is a square matrix. It's good. We have the same number of actions as the number of states. Maybe that was not a coincidence. That's why we got this quadratic expression in the first place. And so if we choose this, then let's calculate. Let's plug in into this expression, right? So let's calculate what J of pi is going to be. The J of pi is going to be, it's mu r pi plus gamma or 1 minus gamma. Well, it's maybe negative. And pi transpose I plus G. And pi. Okay. So this is time to, well, okay. So this is also I plus G pi. There's a time to choose mu, or we already choose mu. So mu was, I think, the uniform distribution. Did we choose it? Yes, we chose it. Right, and so we have to multiply with the identity, the 1 transpose vector. So that's 1 transpose. That's fine. We have to multiply 1 transpose and G. And so what is that doing? So the ith element of that is, this is summing up J. J? No, it's summing up I. So this should be J, right? So multiplying from the left is going to sum up the rows. This is how it looks like. Anyways, this is 3, right? Because we had the 3 regular graph. So 1 transpose G is going to be 3 times 1 transpose. So we have 1 transpose from the identity, 3 times 1 transpose from G. Altogether, we have 4 times 1 transpose over N. And 1 transpose pi is just 1. So this very first part of it, it just simplifies to this constant. So now we're done, right? So if you run your search procedure and you maximize J over this policy class, then we are going to get 4 over N minus gamma, 1 minus gamma, and 1 over alpha of G. So if you want to know whether there exists a vertex set with a coordinate larger than M, then you can ask the same question for whether there exists, whether this the best value that you can get out from here. Okay, this is negative sign here. Is larger than minus 4 over N minus gamma over 1 minus gamma times 1 over M. So this is equivalent to asking whether alpha G is bigger than equal to M, right? So this is the NP-hard problem. So if we can answer questions of this form computationally efficiently, if we can run our search procedure computationally efficiently, then we will surely be able to answer these other questions about the graph. So that shows that this problem is NP-hard. It is actually even harder. So what's the conclusion? Policy search can be hard. Notice that here, the compute time was allowed to depend on the number of states and actions in the MDP. And we managed to create a computationally problem by restricting the policy class, right? So if you're over-constraining things, then what was computationally efficient before, like with the unrestricted policy class, with a finite state MDP, with polynomial time computations, we were good, right? But now we were asking, okay, can we compress? And we find that already, if you're in a finite state action MDP case, if you're doing too much compression, then you create computational challenges that are unlikely to be positively answered. So, and this was for state aggregation, the simplest case. That's pretty sobering, right? But maybe it's not the end of the world. Maybe we are trying something unreasonable. Actually, like this kind of says that like maybe this is too much. And the guarantees that we had before for value function-based methods are not really of the form that, you know, like you would be able to compete with the best policy that is greedy with respect to the set of all value functions or whatever. But they are of the form that if the features are strong enough to represent certain value functions, then okay, you're gonna blow up the approximation error a little bit, maybe a 1 over 1 minus gamma factor here and square root of d over there. But the rest is going to be computationally efficient. And so we're demanding that you find the best policy in a class. Well, this certainly creates trouble, but maybe it's just setting the bar way too high compared to where it has been before. So the next simplest question is then what? Okay, like we want this compression to work, and maybe we also love this objective function oriented thinking, and then we have this j of pi. So what else can we do if not searching for the maximizer? Searching for the maximizer seems to be out of reach. So we can relax the problem. And just look for stationary points. Of the objective function within our function class, within our policy class. So what does this mean? So we know what stationary points generally mean, right? So you look for a point, but the gradient of the objective would be 0. So you can imagine, remember that we are in a finite state action pair case, so the finite MDP case. So in that case, pi is just like this big vector. So you can just take the gradient with respect to this objective. And if you see that the gradient is equal to 0, then you're good. Well, the only trouble is that most of the time, well, you're interested in searching this constraint set, right? And in constraint optimization, it may be that, so you're trying to find a maximum of some function. And like, okay, maybe in general that maximum is really nice and the gradient of it is 0. But maybe you constrain the set, the domain, so your pi is constrained in such a way that the gradient is not going to be 0 there at the optimum solution, right? So here the best possible answer within this constraint set. So this is the constraint domain. Start with a nice function, you constrain the domain, and then this general unconstrained optimization guarantee goes away. The stationary points are not necessarily the ones where the gradient would be 0, but those are the points where you can't make any local improvements to your policy. A global stationary point would be such that if you take your constraint set pi, and you're at this point, little pi in the big pi, and you take any point in this set, any pi point, the objective function wants to push you out of this set. So that means that the gradient is going to be directed out of the set. And so the inner product between the gradient at, let's say, pi star, and the vector that points to pi prime from pi star is negative. It's not positive for all pi prime. Then we could call pi star a global stationary point in the constraint case. If everything is convex, then this is sufficient and necessary for pi star to be optimum. And so this is kind of the second best thing that we can try. So going after points with this property. And then the question is, okay, this is going to fly. So there are two questions. Question number one. Computation. Question number two is going to be approximation guarantees. So computation asks for, is there a computationally efficient procedure that finds stationary points at least under some nice and benign conditions? Right? So for example, we can go back to state aggregation and then ask the question, okay, we know that searching for the best ever policy amongst all aggregated policies is a hard problem, but maybe searching for a global stationary point is not a hard problem. So if you had to guess how to try this search, this computation, what would be the first guess? How would you do it? What would be an algorithm that comes to mind to perform this computational problem or perform this computation? You can type. Gradient ascent, yay, thank you. Yeah, so the candidate, if anything should work, maybe it's gradient ascent that works. So what's the idea of gradient ascent? The idea is that you're here, you're computing the gradient. The gradient is, like the slope of the line, the tangent line to the objective function at the point where you are. So in this case, it's going to point you to the right, and then you make a step. It's a step size. So gradient ascent is going to say, oh, my next point is going to be like the previous point plus some step size times the gradient. Well, this is if you can represent all the policies, but very often you have a policy parametrization that you're working with. Like in the case of the Boltzmann policies, there were these weights, right? Like, where is this? It's been a while. Right, so there are these weights, the W, right? And so all the policies are represented with the W, so let's take the gradient with respect to the W. So that just means that you take the gradient of J with respect to the policy, and you take the gradient of the policy with respect to W, right? Like chain rule. And then you make the step in the W space. So you could also write that. So this is just the gradient of the objective with respect to W, where you are this policy whose parameter is WT. Well, I don't know whether you can see my scribbles over there in the corner. Which raises questions about, okay, is it going to matter how we choose this parametrization? How to choose the step sizes? Can we make this gradient as an idea work? All right, so that's the first type of questions, and the second type of questions is, okay, we do all of these calculations for what? Like at the end of the day, we want to have some guarantees. So it would be nice to say something like, if pi star is a global stationary point, or a stationary point, like it's where gradient descent is going to find global or not. It finds a stationary point. Then does it follow that if you take your objective function, which was what, mu, and all right, so let's not call this pi star. It's very confusing if we call it pi star, because pi star was reserved to the optimal policy. So let's call it pi st. Maybe I could have left the. So I want the policy that is found to be a good one. Compared to what? Well, it's compared to the optimal policy. We like to compare to that. And then the question is, what can we say here about the interplay between the MDP and this policy class, or the features? So that's the type of result that we were like talking a lot about in connection to, policy iteration, value iteration, polytech, whatnot, right? Like whether this model, like these approximation errors of like how well the features are capturing the optimal action value function, or all the action value functions, whether they get multiplied with 1/1 minus gamma or square root of d as well, and like how big is this quantity? Can we make it small? So you can ask the same question here. All right, so there are these two classes of questions. But before that, we should also, well, okay. So with computation, I think that it is really a study of these days of how well gradient ascent can work in this MDP context. And here I would, okay, so there are the questions about this, right? So if you want to execute gradient ascent, then maybe you should know how to obtain the gradient. So the gradient is not given to us. If you have access to a simulator, maybe you can run some simulations. How expensive it is to get a good estimate of the gradient? So that's the very first question. You have a large MDP. You don't want to do exact calculations. Can you just get some reasonable estimates of the gradient with respect to your favorite policy class? So how to compute this with a simulator? And then, of course, people study this in the online case, the batch case, and so on and so forth. But the easiest of all of these cases is always if you have access to simulators. So we should talk first about that. So that's question number 1. And sub-question number 1, it's 1.1. And then 1.2 is like, okay, what exactly is like, which algorithm are we going to run? And can we be agnostic to pi? If you have a policy class which is smoothly parameterized, can we just like somehow run with that and then prove that we will converge fast to at least a local optimum stationary point? All right, so to break this big tension about this question, I will bring up one recent result that we discussed a little bit on Slack. This is this paper, softmax policy gradient methods can take exponential time to converge. It's a bunch of people, Jin Li, Yuting Wei, Tuji Qi, Yuntou Guo, and Yuxin Chen. And they took the burden of looking at softmax policy gradients. So this softmax policy gradient is exactly this Boltzmann class, this linear parametrization. But the features are just like the trivial features, the tabular case, right? And they took the burden of looking into whether policy gradient, this gradient Ascent search, can converge at least with some initialization, with some nice choice of mu, this initial state distribution efficiently to a stationary point. And it's not an easy thing. Well, okay, I can't go to the next page. So that, oh yeah, there you go. It's a lengthy proof, but they have this result that I wanted to highlight that should again tame a little bit our expectations. Like this shows that policy gradient is not really a panacea in the sense that can be really sensitive to choices like what is the class of policies that you're working with and how you're parameterizing that class of policies. So if you happen to choose the wrong parameterization, then really bad things can happen to you. So the result that's shown here is this. It's kind of like in the middle. I can't write here. But so it's theorem 1 that says that you take the uniform initial state distribution, which is supposed to be a benign state distribution, a uniform policy initialization. That means that you're in a tabular case. So every action in every state has equal probability, and you have access to exact gradients. Then for some universal constants, which are positive, and every discount factor, which is big enough, and every time that the state space is large enough, you can find a gamma discounted MDP with this state space such that the number of iterations that policy gradient with the softmax parameterization needs is at least this 1/eta times the coordinate of the state space raised to the power of like 2 to the effective horizon. So it's like super exponential. Well, okay, you could just say that, but it's, I guess it's exponential. So if you choose eta very small, then this is going up. You cannot choose eta to be too large, because then policy gradient is not going to converge. So there's going to be an absolute limit of how big eta could be. I think that should be added to this result. So that should tame our expectation of what to expect in terms of generality of policy gradient methods. So so this doesn't work. Nope. You have to be careful. Well, either you have to maybe change the vanilla PG method, or you have to be really careful in choosing this policy class if you want to stick to the vanilla PG method. And how to change the PG method. One idea that appeared in the literature a while ago is known as natural policy gradient. In a way, it's almost like saying that, well, the general idea of natural gradient descent or gradient ascent, natural gradient methods, is that you want to be parametrization invariant and still following the gradient. So here we had this objective function j, okay, and then we chose a parametrization. And if you take the derivative of the whole thing with respect to the parametrization, I already told you that it's like, okay, take the derivative of j with respect to pi, plug in pi w, and then multiply that with the gradient of pi, the policy with respect to w. And then you're going to follow this derivative. But like this, if you make steps in this direction, it's generally not necessarily the same as just taking steps in this direction. So you could try to, like you're in this W space. It is your W. And then it maps to this policy pi. All right, so this is the PW parametrization. And here, this J function is giving you a direction. And then you can try to map it back. And then some way of mapping it back is this chain rule. But there could be other ways. Like you could try to search for the exact W that gives you the exact same point where you would go if you follow the gradient, irrespective of that you are constraint in the space, and you do this with a local approximation. So that's kind of the idea of the natural gradient method. And at least it's like maybe it raises the hope that this could be agnostic to policy parametrization. And why that might be a good thing is because policy gradient, you can show that it's not a terrible algorithm in the tabular case with the trivial parametrization of the policies, which is just like looking at policies as, big vectors. So if you don't introduce this exponentiation trick, then this hardness result that we have shown for policy gradient methods goes away. And so maybe it's a good idea to introduce something that undoes what the parametrization introduces. All right, but I'm going to leave this to the next time. So next time we're going to start talking about maybe this first question. I think that would be good. How to calculate the gradients, and then we're going to talk about a little bit about this natural policy gradient idea, and then we're going to touch on these approximation guarantees as well. Under what conditions can we have these approximation guarantees? What we had before for a function approximation, we had varying degrees of results. So for the positive results, we had to assume either that all action wave functions are well represented with a small error, or we assume that the state value function, so that was tensor plan the last lecture, the state value function is linearly representable. And you might ask, okay, like if the optimal policy lies within the class, so that's like the second case, can we get approximation guarantees for the stationary points? And the other question is, if we, for all policies, somehow something nice happens, like what does it correspond to that the action wave function lies in the span of the features? Like, we need to talk about that. So if something nice happens for every of the policies, then maybe you can get some results similar to what we had before. All right. Okay. Any questions? I think I stop here. A little bit over time. Not too much. Okay, maybe we can stop recording, and then even after we stop recording, you guys want to ask questions, then